Topic 4.5 Heat exchange or sensible heat. Heat capacity. When a Q amount of heat energy is given to an object, if the temperature rise is theta, then the Q is proportional to theta. By introducing a proportionality constant C, we can write it as Q equals C theta. Here the capital C is called the heat capacity of the object. Heat capacity of an object can be defined as, therefore, the amount of heat required to change the temperature by unit. SI units of heat capacity, capital C, will be joules per Kelvin. Dimensions of capital C equal to the dimensions of joules, that is m L squared T minus 2. If we further go into this heat capacity of an object or a given amount of substance, we can see that heat capacity is proportional to mass and mass of material. Heat capacity of a single material, heat capacity of a material is proportional to its mass. We double the mass of the same material, heat capacity is doubled. By introducing another proportionality constant, simple C, we can write this heat capacity capital C as simple C into mass M. Here, simple C is called the specific heat capacity. Q equals capital C theta, which will be in turn Q equals MC theta. Here we use simple C. The simple C, the specific heat capacity, can be written as capital Q over M theta. Therefore, we can define the specific heat capacity as amount of heat energy required to rise the temperature by unit of unit mass of the material. SI units will be joules per kilogram per Kelvin. Dimensions L squared T minus 2. Both above quantities, heat capacity and the specific heat capacity, can be applied for solid state materials and liquid state materials. But when we come into gaseous state materials or gases, quantity will be slightly changed. When the similar quantity applied for gases, it is called the molar heat capacity. There are two types of molar heat capacities for a given gas. That is the molar heat capacity at constant pressure Cp and molar heat capacity of constant volume Cv. Similar type of equation can be written for gases, if we add the heat to a gas under constant pressure conditions, the equation will be Q equals NCP theta. Yeah, N is the number of moles of gas. Cp is then called the molar heat capacity of the gas under constant pressure. On the other hand, if we add the heat for the gas under constant volume condition, then it can be written as Q equals NCV theta. Yeah, N is the number of moles. CV is called the molar heat capacity of the gas under constant volume. Q and theta are the amount of heat energy added or deducted and temperature difference respectively as in previous cases. Cp can be written as Q over n theta and Cv also can be written as Q over n theta. Cp can be defined as the amount of heat required to change the unit temperature of a single mole of gas under constant pressure. Equally, Cv can be defined as the amount of heat required to change the unit temperature of a gas, of a single mole of gas under constant volume conditions. SI units of Cp is joules per mole per Kelvin. Same unit C is therefore Cv also. The ratio of Cp and Cv is denoted by gamma. Value of gamma for a given gas depends on the atomicity of the gas. Atomicity is the number of atoms in a single molecule of gas. Here comes the experiment determination of specific heat capacities of solids by the method of mixtures. Newton's law of cooling. Newton's law of cooling states that under forced convection conditions, for small temperature difference between a body and its surrounding, the rate of cooling of the body is directly proportional to the temperature difference and the surface area exposed. So, there are several conditions for Newton's law of cooling to be true. This is true only under forced convection conditions. Natural convection, under natural convection conditions cannot be applied. And also this is true only for small temperature differences. For larger temperature differences, this cannot be applied. The rate of cooling, the rate of drop of temperature is proportional to the temperature difference between the cooling object and the surrounding environment. Temperature difference, in other words, the excess temperature of the object. And also, the rate of cooling is proportional to the area of the surface area of the object. The greater the surface area, the greater the cooling rate. That is the Newton's law of cooling. We can express Newton's law of cooling mathematically as follows. Here, the rate of cooling d theta by dt is proportional to temperature difference between the object and surrounding. Theta is the object temperature, theta r is the room temperature. Again, the same law states that cooling rate is proportional to the surface area of the object. A is the surface area of the object. So we can express these two conditions in two equations. Combining these two equations and introducing a proportionality constant J, we can write this as a equation d theta by dt equals J A theta minus theta, where J is the proportionality constant. Now we will combine our previous equation Q equals mc theta into this equation. Since Q equals mc theta, we can write dq by dt equals mc d theta by dt. Combining this equation and Newton's law of cooling, we can write dq by dt equals mcja theta minus theta r. Is the mass of an object, C is the specific heat capacity of the material, it's a material property, J is a proportionality constant, A is the surface area of the object, again a constant for a given object. Therefore, MCJA product altogether is another constant. This equation can be derived combining the Newton's law of cooling and Q equals mc theta equations for a given object. And here comes the experiment: determination of specific heat capacities of a liquid by the method of cooling. And that is the end of topic 4.5, heat exchange or sensible